So we've been talking about complexity, which refers to complex systems, and these complex systems are high dimensional and random-like, but they need not be random, and most often they are more chaotic than random. So complex is not necessarily random. In fact, we'll think of complex, but not necessarily random. So complex data comes from complex systems, where a process or a dynamical system is complex if it has many degrees of freedom, high dimensional, both chaotic and regular variables interacting nonlinearly, an underlying structure, its topology that spans multiple scales, and the capacity to produce emergent behaviors, interactions on one scale producing phenomena on another. Let's look at these two further. Chaotic is not random. Processes with structures that are multi-scale, ordinary motion on such a complicated structure is often chaotic, and chaotic variables model these chaotic motions. In contrast, ordinary structures, circles, lines, and whatever, lead to regular variables. Random variables are neither chaotic or regular. They obtain values from a random process. There is no underlying structure. Let's look at two examples of what I mean by complex. A point x, y, and a unit square we'll say is in class 1 if in its binary expansion of x plus iy the digit 1 occurs with a greater frequency than 0.25, and it's class 0 otherwise. And this is what we get, this very complex image, which is a very difficult classifier problem. Now let's suppose that we take another example, one where we have some iteration. A point is class 1 if Newton's method for z to the fourth minus 1 converges to a real root, 1 or negative 1, from the initial point z naught equals x plus iy. It's in class 0 if z naught equals x plus iy leads to something other than a real root under Newton's method. And it looks something like this. Again, quite complicated. So a process is chaotic if you have sensitive dependence on initial conditions, which means points arbitrarily close together may lead to motions which are completely different. We can see that in this example of the Newton's method classifier problem. We have in this little magenta square points that are both black and green. But all the green points, once we iterate with Newton's method, are going to end up at one of the two green dots, 1 or negative 1. In fact, they're going to end up at negative 1. All the black points move to other black points. So even though we've got a green and a black point that are very, very close together, they end up in very different parts of the plane. Now, points close together may be at different scales on the underlying structure. This is one of the reasons you can see sensitive dependence on initial conditions. Also, we get chaotic if there are no stable periodic motions. There's no cycles. And also if we get topological transitivity. Every part of the underlying structure leads to every other part. So what's the difference? Well, let's look at random versus chaotic. Random is non-deterministic. A random process sampled exactly the same way in two different trials produces two different sets of data, but with the same information on average. Chaotic is deterministic. If we sampled precisely the same way in two different trials, we would get precisely the same data, although any tiny variation will lead to something much different. The law of large numbers. We have isolated subpatterns of random processes are not significant because in the long run it's only the averages that are meaningful. But in chaos, each isolated subpattern is information at some scale about an overall multi-scale underlying structure, known as a strain detractor. So chaotic and random are not the same. However, if it's highly chaotic, then it's also practically random. So highly chaotic means it's complex and extremely high dimensional context. Large numbers of unrelated independent variables acts like large numbers of trials of random processes. So chaotic and random are not the same. Random has a distribution but not a structure, whereas chaotic has a structure and a distribution. Now, emergent phenomena, if we have multi-scale structures, then interaction across scales can produce new behavior not associated with a single scale. Small scale activities can imply large scale outcomes. Genotype can imply phenotype. Locally simple processes, they have to be nonlinear however, can produce globally complex outcomes. Emergent behavior in a nutshell comes from the fact that nonlinear processes plus multiple scales gives us complex systems. So, complex is not random. A complex system is a mix of chaotic and regular non-chaotic variables. Chaotic emerges from deterministic, highly typical circumstances because it occurs naturally. But highly complex is practically random. So we'll see that low dimensional complexity is useful, but high dimensional complexity may be best to just think about it probabilistically. So complex systems and big data. Big data is often an attempt to study emergence. We collect data about genotype so we can say something about phenotype. We collect data about pathogens so we can say something about epidemics. Individual agents on a small scale apply a global collective behavior. Twitter, recommender systems, Facebook, social networks, economic activity. Videos going viral are large-scale outcomes due to small-scale individual communications. But big data often contains more than complexity. There does tend to be some randomness or noise. The noise may obscure features at some scale. Feature engineering is always necessary. Pre-processing, for instance, may be necessary to remove noise that is obscuring useful information. And feature selection may be necessary to remove features that don't contribute significantly. So let's look at this idea of feature selection. We had the grades example. We saw that exams 2 and 3, in particular exam 2 is the one we focused on, and saw that it was a turning point. And we said that in fact you can use exams 2 and 3 to predict if a student's going to pass the course. Now this is not just heuristic guessing. We can do this quite rigorously. In sklearn, we can use the select k best, and we're going to select the 2 best, and notice that the 2 best from our select k best object fit is the exam 2 and 3. We can also incorporate a statistical test. In this case we'll do the chi-squared test, and when we do that, notice now it predicts that exams 1 and 3 are the best predictors. So that exam 3 seems to have some significance. But don't forget about bias. Bias, rigorously spoken, bias is the expected difference, expected as in expected value, the expected difference between a given statistic and an estimator of that statistic. If the bias is 0, then the estimator is said to be unbiased. For example, if you average over n independent trials of x, then that converges to the expected value of x, and therefore it's an unbiased estimator of the expected value. But estimators which do not use the topology of a big data set are almost certainly biased. We need to use these with caution. So, insights into big data. Much of what we call randomness in the real world is actually chaos. Is it random or is it chaotic? A better question is, how are we going to actually get information from the data? Are we going to try to use the data to reveal some aspect of a complex underlying structure? Are we going to look for emergent behaviors? Then it might be better to think in terms of chaotic and complexity. But we need enough data to allow for that complexity, and we need enough complexity to allow us to reveal the structure. So we also know now, in some sense, what big data is. So just to summarize, we know it's big data if it is a high volume of data obtained from a system that we know to be complex. It's collected with high velocity at one scale in order to address a question at another scale, usually high velocity at a small scale in order to answer questions at a larger scale. And randomness alone, even if there is randomness, then randomness alone can explain the high variety that we see in the data.